Okay, it looks like it's 1 o'clock, and that was the promised time to start. So why don't we go ahead and get started while I see still several people coming into the webinar, but in respect to everybody's time and trying to start on time and so on, let's get rolling. So I'm Jim Mielke, Professor and Chair of Fire Protection Engineering at the University of Maryland. I'll introduce myself a little bit more in a little bit, but I want to welcome you to this webinar that I'm having. I get a chance to introduce. Basically, Tracy Hannigan will do most of the discussion on this, so it's a pleasure to have been able to talk with her a little bit over the last couple of weeks planning for this, and I have to say I'm as interested in hearing what she has to say as I think many of you registered for the webinar. There is AIA continuing education credit that's available. We'll post this information later, so you don't have to quickly jot it all down right now. But for those of you interested in AIA credits, that's available. We do have some objectives for this, and looking at the transmission methods for COVID-19 throughout a building and how the HVAC system perhaps impacts that. In short, want to look at how the built environment can be modified in various ways to try and mitigate that risk. Look at the impacts of dry indoor air on the human body and as well as the transmission of the disease-causing microbes, and then describe some new research in the area. So again, for those of you so interested, there with AIA continuing education, there is a link to travel to, and you'll be asked to input that information, such as we provided you a couple of slides ago. And we'll provide that info for you through the chat. So just very briefly, so as I mentioned, I'll be doing a very brief intro, and then Tracy will be covering the other four topics here of looking at transmission pathways, indoor air environment impact on our health, HVAC system resiliency, and a conclusion. So just very briefly about me, I'm Professor and Chair of Fire Protection Engineering at the University of Maryland. My involvement with this webinar came about, I guess about maybe a little more than a month ago now, where I was talking with one of Tracy's colleagues at Coffman Engineers and about some things we might do jointly together. We did a webinar 2 weeks or so ago, 3 weeks I guess now, on pedestrian planning, and this topic came up that I thought was really interesting, where we talked about some software that gets used in smoke control systems that I have a fair amount of involvement with, a software called Contam that was originally put together for indoor air quality analyses. I'd had most of my experience with smoke control, but have come to find out that it has some relevance here, and got introduced to Tracy as a result of that. So it's a pleasure to be working with the folks at Coffman once again and doing a collaboration. And I've got my other instructor.
Thanks, Kat.
As it says in my specialties, I get involved in smoke control system issues quite a bit, otherwise looking at response to people to fire and then advanced fire detection methods. Tracy?
Right. I'm Tracy Hannigan. I'm a principal at Coffman Engineers. I've been at Coffman for, 24 years, something like that. Went to school at the University of Idaho, and I do a lot of work in healthcare design, laboratory work. I'm currently the chair of ASHRAE's technical committee for healthcare facilities, and I'm a voting member on the Epidemic task force, which ASHRAE formed in early March after the outbreak of the pandemic. I do a lot of infection control work and help coach clients and friends and family too on being prepared for epidemics.
So as we look to reopening considerations of our businesses, our campuses, our entertainment centers, so on and so forth, what's driving that? And I think it's fairly evident in the media every day that there are certain business needs and needs of our economy. And let me be able to see the screen. So, but you know, there is a risk of transmission as places get reopened and we you know, come into close proximity to people still 6 feet away, but we're in the same indoor air environment perhaps with people, and need to be cognizant of what mitigation efforts there are, of which social distancing is one, but there are others that we're going to hear about today. As we look for developing plans for reopening, so this is really the second of a two-part series of webinars where the first one we looked at and covered a lot of the individual behavior issues, again, that you've heard a fair amount about from CDC or your state health departments about you know, individual behavior and needing to do health checks. If there's anything close to a question of being ill, there are face coverings, of course, and hand washing that becomes very prominent, not touching the face, you know, those kind of basic things. Looking at physical and social distancing, this was the topic for the previous webinar that I had the pleasure to collaborate with Robert Gerard, one of Tracy's colleagues at Coffman Engineers, and looked at physical and social distancing, looking at developing pedestrian plans for buildings, using some software to help those decisions that Robert covered at length. And then, in fact, we're involved in a significant effort at Maryland with, I'm involved with a team of students, both graduate and undergraduate students, to apply these simulation models, a simulation model called Pathfinder, to developing pedestrian plans for campus buildings, for an array of campus buildings, as well as the football stadium, should things happen that you can even play college football at some point in the near future. You know, I guess I would say if we don't get to play this year, the team will go undefeated for the first time in a long time. So, you know, but anyway, we'll say just as a little bit of a shout out, a little advertisement. I do have a lecture that I'm doing tomorrow as part of our summer lecture series for faculty tomorrow afternoon, where I'm going to be talking about the pedestrian plans and talking about a couple of the case studies of campus buildings. But that's tomorrow at 1 o'clock. For anybody that's interested, I'll put the link in the chat. I think there's still ample time to register for that. Anyway, the next piece of that is to look at the role of the building indoor air quality and the HVAC system as all part of this plan to reopen our businesses. So with that, I want to turn this over to one of the nation's experts in this area, and that's Tracy Hannigan.
Thanks, Jim. All right, very happy to be here. So the enemy is also here. We've got spillover from infectious diseases. And this book here is a really great one, a favorite of mine by David Quammen. So if you're interested in learning a little bit more about infectious diseases and how they tend to spill over from animals into humans and how the decisions we make in terms of our economics, our politics, just our daily lives can influence the likelihood of spillover, this is a really great book to read. In February, I was in Orlando at the ASHRAE annual meeting, and we were talking in our infectious diseases subcommittee about the Wuhan virus at the time and watching it pretty closely. This was a screenshot that I took at the time, pulled it off my phone. We had a whopping 24,000 cases. And you'll notice my map is just zoomed in on China because that's really where the crux of the outbreak was at the time, and we were closely monitoring the cases. I remember it had been 8 in the US and then popped up to 11. And this was a week ago when I was meeting with some clients and sharing some information. We were over 14 million cases a week ago. And just when you thought that, well, maybe things couldn't get any worse than that, because that's pretty bad. That was last night. We were over 16.5 million cases that we went up to in just a week compared to the 14 plus change that we had just a week ago. So enemy's definitely here and we're in the thick of things. But we're learning a lot. There's a lot of information that's been shared, that's been researched, still more to know. And I think it's important that we share and talk about what we know, what we don't know, and then what we think. and to distinguish clearly between those things. So the SARS-CoV-2 virus is the virus that causes the disease COVID-19, and it's very small, but most of the time that very small particle is attached to droplets, like when we cough or we sneeze or we speak, and those liquid droplets are much larger than the plain virus itself, and so that makes it easier to catch in a filter, which is good. We learn a lot early on from super spreader events when we have outbreaks, and things like the Skagit Valley Choir, where there were a lot of individuals in March that were aware of the virus, went to a choir practice for a couple hours, they spaced out, they did not shake hands, they used sanitizer, and in the conclusion of that event, many of them went home unknowingly infected, and they had a large number of the attendees that were infected in that case. The Gangzhou restaurant is another well-known super spreader event, and then lots of other examples of this happening, especially at barbecues, weddings, funerals, churches, those kind of places. And so I put a link to some super spreader events that were studied you might find interesting to go peruse. The University of Nebraska Medical Center published a study, and this was pretty early on, where they looked for viral RNA of the SARS-CoV-2 virus at their medical center where they'd been treating patients. And they found the viral RNA in many locations, so it gave us a sense of how those particulates are moving around a space. Something to keep in mind, though, is that they find viral RNA, but the presence of it doesn't mean that that RNA is in fact viable or infectious, could make somebody sick. It's very difficult to collect RNA and test it to see if it's still viable or not in a manner that doesn't destroy the virus in the process of just trying to perform that test. So right now, we know that RNA has been in many places, but we don't know how far it can go and still remain viable. But I am aware of some studies. There's one paper in particular that I know that's in peer review at this moment, so stay tuned for more on that. I don't know if you know that one way to track the transmission of infectious diseases around the world is to study the sewage in airplane toilets. It's kind of gross, but it's effective. Toilets are something that our infectious diseases subcommittee talks about pretty regularly. There's a toilet plume that comes up, and studies have shown that you can have infectious pathogens like C. diff in a toilet, and you can flush that toilet multiple times and still be releasing particulates into the air that can then land and settle out on adjacent surfaces. So there's been suggestion of SARS-CoV-2 also being transmitted through fecal matter and therefore subject to being spread by a thermal or a toilet plume. There is a new calculator that has been developed by some of the bioscience guys with Homeland Security. Here's the website link. They did some studies about the virus viability in different conditions, and I saw some early papers from them that were kind of a prelim test result back in April. Since then, they've developed this calculator. Real important that you read the background and the caveats on it, but it shows the impact of UV light, temperature, and relative humidity on the life survival time of the virus. And I say life, viruses technically aren't alive. Sometimes we say viable, but sometimes we just say they're alive or dead. This is an example here if you want to compare, like here's a 75°F, low UV light, 20% relative humidity, and at 50% half-life is about 21, almost 22 minutes. You bump the relative humidity up to 40%, keep the other conditions the same, the half-life goes down to about 15 minutes. Now keep in mind with this calculator, this is not exact. This is from some studies that have been done with SARS-CoV-2 and good measurement techniques, but there are other parameters that could come into play, and some of the data have been linearized for this calculator. This is a study that was published in a preprint not very long ago with the Oregon Health and Science University. This group of research has access to the facility where they've been treating COVID patients, and they looked to see if they could find RNA in the HVAC units that were serving the building. So they looked in the air handler. This system has a much higher percentage of outside air than is required by code minimum in ASHRAE standards. And it has higher levels of filtration also. They've got a MERV 10 pre-filter. Oftentimes that's only a MERV 7 or 8. And then the final filter is a MERV 15, which is higher than the MERV 14 minimum. But they sampled before the pre-filter, they sampled before the final filter, and then they sampled downstream of the final filter at the supply dampers. These were the results that they found. They found quite a bit of viral RNA as expected above the pre-filters, less of it in front of the final filters, and then they still found a pretty good amount of it on the supply air dampers, meaning that those particulates of virus probably dried out as they were passing through the air handler, became smaller and smaller, and filters are good, but over a long period of time, some smaller particulates are going to pass through them. They're not 100% blocking of all particulates at every size. So these results aren't super surprising, but it is good to know that hey, we've got to be aware that RNA can be traveling through these systems. The next step that they're doing is to look and see if they can find viable virus and not just the RNA, but whether or not it could be infectious or not. I did have a chance to follow up with the researcher, the lead one on this, and learned they did check for things like filter bypass and felt pretty confident that the filter integrity was really high. But there's a lot of further research that we want to know. For healthcare facilities, there are aerosol generating procedures that we know put people at risk, doing a bronchoscopy, for example, or intubating a patient to be put on a ventilator. But we don't have a great sense for how much airborne transmission is going on outside of those known aerosol generating procedures. We want to look for the presence of viable virus. We don't know what the infected dose is. It's going to vary depending on a person's health, but we'd like to get an idea of the range of how much exposure someone needs to have before they get infected. And looking at the particle sizes in different situations, what they might do, how they move in the space, and thinking about environmental conditions and what would maybe reduce the lifespan or viability of a virus, or what enhances and increases it. So the research that we're looking to do, and ASHRAE is supporting and funding some of that through donations, helps us decide on priorities. So this little comic that I love, it makes you think about how sometimes our priorities can get mixed up. And when I do HVAC design, this is an area where I like to really talk openly with my clients, my architect clients that I work with, and building owners, facility directors that I work with, because sometimes we have ideas of priorities that differ from one another, and we really need to come together with the best solution overall. So how do we change the built environment to mitigate risk? And can we even do anything to make it better? Well, the short answer is there's a lot that we can do to make it better, but we still need to keep in mind the basic things like wearing masks, washing hands. The close droplet transmission is still very important, and we're still trying to understand the impact of aerosol transmission, but there's a lot that we can do to help make things better. One of the areas that's most underestimated is the airflow pattern in a space. So there are things we can do to change that airflow pattern. If we have infectious air from somebody who's been coughing, sneezing, or even just talking, and the air current moves from them across another person before it goes into an HVAC system or out an exhaust grill or something like that, that next person in line is at risk. And so we can do things with the way we lay out furniture in a space, the way we configure supply and return or exhaust grill locations and diffusers. We can try to do source control. That's more common if we're working in a healthcare facility, where we can do like a ventilated headboard over a patient area to try and gather their exhaust. Excuse me. And certainly recirculating HEPA filters inside buildings. There's also the opportunity to increase filtration level if you have a home or an office where the filtration level isn't very great. The ASHRAE Epidemic Task Force is recommending upgrading to a MERV 13 or better wherever possible. You have to look at your HVAC system, see if it's compatible. But good quality MERV 13 filters can, in some cases, have less pressure drop across them than a poor quality MERV 8 or MERV 11 filter. And so you may be able to find a filter to replace that won't tax your fan horsepower capacity beyond what it's capable of doing. And then certainly increasing the amount of clean outside air being supplied to a space. And both of these, filtration and clean outside air coming in, being increased, have advantages. And I want to talk a little bit about those and the pros of doing both. So filtration versus outside air dilution. This chart shows the cost of changing filters on an average size little office building, and what that does to this index that has been created. It's like a relative risk of getting an infection. So really high risk of infection if you have poor filtration, like a MERV 4 to a 7. But when you start getting into a MERV 13 or a MERV 14 filter, you've really dropped the relative risk substantially. And then you can continue to improve the filtration quality in a unit all the way up to HEPA filtration. It adds quite a bit more cost. It does decrease the relative risk of infection, but not substantially. Once you get to a MERV 13, you're doing pretty good. And then the other colored lines show increasing ventilation, which is of course going to cost a little bit more than adding filtration, but we'll come to some other benefits of that as well. But you can see how adding additional outside air is really going to drop that risk of infection. So when we think about which should we do, we like to make sure that a place has at least a minimum amount of outside air, and then try to grow that some, and then also improve the filtration as much as possible. So you have to look at each scenario to see what's the best trade-off and how much you can accomplish. This is another chart to show the benefit in terms of health and mortality of people by improving the filtration from something like a MERV 6 or 8 all the way up to a MERV 16 in this chart. The filter costs are really small compared to the benefits in terms of morbidity and mortality for humans. This is a pretty recent study from 2015 that was published. And then lastly, benefits of outside air. There have been so many studies about the benefits of increased ventilation. Keep in mind that the ASHRAE standards are a bare minimum, and it's highly recommended that you think about going higher than what those bare minimums are. There's a lot of studies. This is one in particular that's really comprehensive. It was published in 2015 about the environmental health implications of increasing that ventilation in office buildings. There's some great research. It's a good article to read. The conclusion on it is really that the benefit of enhancing that ventilation really exceeds the cost to do so. And in fact, they even say the increased productivity is 150 times greater than the resulting energy costs. And their conclusion really was, we don't see why more people aren't increasing their outside air rate because the benefits are so significant. So continuing on about how we modify the built environment and reduce the risk of getting infected and transmission, there's also disinfection that can be done. People are familiar with things like vaporized hydrogen peroxide. There's also a lot of information out there about things like bipolar ionizers, which I just caution people to really be careful about evaluating the technology and think about how tests were done. Are there lots of pieces of information in peer-reviewed literature versus third-party independent tests, which are really just labs that get paid to do testing for a manufacturer? Are the tests conducted in a situation that's really similar to the way the product is intended to be used? And is there a control comparison? Like if somebody tested something and said, well, a lot of virus died, did they compare it to the same situation with the product turned off? Because some of the virus is just going to naturally get inactivated over time anyhow, and you really want to compare to a baseline. So just some caution on evaluating that technology. Keeping in mind toilet rooms, if you can have lid on a toilet seat, that's really important to put that lid down. And then thinking about environmental conditions, I mentioned this is an area of active research. So I want to spend some time talking a little bit about what those are and the impact on that. So I was going to take a quick peek. Someone was asking if higher airflow is better than filtration. Certainly having a good number of air changes is important, and thinking about having a good ability to have fresh air moving through a space and not having dead spaces. where contaminants could collect and increase in terms of concentration. So looking at that overall room air distribution is really important. But once you get about 2 air changes per hour of outside air in a space, that's kind of a minimum. And then I would look to increase the ventilation, the filtration level if you were down at like an 8 or 6 or something like that, trying to get that up to a MERV 13 minimum. And then once I hit a MERV 13 minimum, I'd go back and look at trying to increase the overall air change rate and the outside air percentage to a space, just as a general guidance. But again, every situation is going to be unique, so you really want to have your situation evaluated. So what makes a difference in whether or not, this cough is infectious or not? So I'm going to see if I could get my little screen to play this. Yeah, here's a great image. So this is a research group, the Lydia Borobia's group that's studying the aerosolization of sneezes and coughs. So when we think about this particular cough or somebody else coughing or sneezing, we know that it's really a lot of liquid, not very much in the way of particulates. And what happens is the environment that someone coughs or sneezes into has a big impact on how that cough responds and acts and has the potential for transmitting infectious diseases. So if the air is really humid, then those droplets tend to stay in droplet form and they're heavy and they settle out, and you can clean the surfaces and wipe things down and they don't travel very far. If the air is really, really dry, then those droplets that come out of a sneeze or a cough tend to desiccate a little bit, and then we're left with smaller infectious droplets that will travel further. So to give you a sense for that, if we have droplet diameters that are really small, like 0.5 microns or so, those can float for hours to days in the air when the air is dry, whereas larger particles are going to settle out in a matter of seconds. So the moisture content of the air around you really makes a difference. I want to share a little bit of research that I came across from a colleague of mine, Dr. Stephanie Taylor. She was a physician helping with the microbiome project, and it was at a hospital in Chicago. And she used to be a pediatric oncologist, and then she noticed that the built environment was creating infections in some of her patients and killing them instead of them dying from their cancer. And so she went back to school and got a master's in architecture and works on how the built environment affects patient and occupant health. So this study was a microbiome study. It was a year-long evaluation of patient room environment. So there were 5 med-surg patient rooms in a nurse station and 5 oncology rooms in a nurse station. And they swabbed hands and surfaces and floors and tracked how the microbes moved through the space. And they collected a whole bunch of data on things like what the room traffic was and the air change rate, whether or not people were washing their hands and their temperature. The other thing that happened is that they ended up sending Dr. Taylor the patient room outcomes in terms of their healthcare associated infection rates. And so she looked at that information and had that analyzed by a statistician to see if any of the data that they collected correlated to the healthcare associated infection rate. And what they found is that when the patient room relative humidity went down below 40%, the healthcare associated infection rate went up. And it was strongly correlated. They didn't really believe the data, fired the statistician, got a different one, and showed the same results. So this is really legitimate. The other thing is that the diversity of the microbes also patterned the relative humidity. So we had a greater diversity of microbes in the space, which is healthy because we want to have a really good diverse microbiome. Those diverse microbiomes are less pathogenic than ones that are getting really isolated and selected for. So healthcare associated infections going down once that relative humidity gets up above 40%. There's also a study in 2018 that covered a 4-year time span of residents in a memory care type facility. And we know right now with COVID-19 that we've had a huge number of deaths from our elderly friends and family that are living in assisted living, nursing home, skilled care type facilities. So this study looked at patient infections and tried to compare the environmental data to see if there was any correlation. And the results showed that respiratory and gastrointestinal type viruses were lower in the 40 to 60% relative humidity range. The relative humidity didn't really impact things like urinary tract infections, which makes sense because that's more of a contact type infection that's developed, but really a big impact on the respiratory and gastrointestinal infections. So at this facility, they've gone back in and installed humidifiers, and they're collecting data to show what the impact then is after they humidify those spaces to maintain at least minimum 40% RH. And this study was conducted by the Mayo Clinic. It was published in 2018, where they took several students, whole classes of preschool kids, and had 3 rooms where they did not humidify the space. So it was dry, 20% relative humidity air. And then they added humidifiers and humidified 3 of the spaces. And they looked for influenza virus. They found a lot more influenza virus in the space that had the dry air. Then they also looked to see if that influenza virus was infective or not. And they found much more infective virus in the dry air. And then the best marker of all is what's the outcome of people's health. And they found a much greater incidence of children who were absent due to influenza type symptoms. They weren't actually tested for influenza. There's some HIPAA rules with that, but the kids that were out with a respiratory ailment that seemed similar in symptoms to influenza, and much more of those in the dry air. Last study that I want to show you is a study that came out from some researchers at Yale. This was published just in May of 2019, where they did some investigation about how the dry air might impact our own biological responses to infection. So they did this study with these special mice. They had to use mice because part of the study was cutting up the lung tissue and looking at it, and we don't do that with people. But they took a chamber and put the mice in this chamber and kept some of the mice either at 20% relative humidity and some of the mice at 50% relative humidity for a few days, and then put a whole bunch of influenza virus in the space, and then left them in there for about a week, and then took them out of the chamber to see how they responded. And what they learned is, like in humans, we have protective mechanisms to keep us from getting infected. So they studied how this happened in the mice. We have cilia in our throats, in our lungs, that push particulates up and out. These little hairs are constantly moving and clearing our airway of infectious particles and debris. When the air is dry, the mucociliary clearance mechanism is greatly diminished, and they could show these mice that the ability of these cilia to clear the airway was really reduced. If something gets past there, our body's immune system responds initially with interferon, which is just an initial early immune response mechanism. And when the air is 20% versus 50% for the mice, their amount of interferon that responded to contamination in their lungs was also greatly reduced. Then when they got infected and they became sick with influenza, the ones that did become sick, there were a lot more of them that were sick in the dry air compared to the 50% RH. And they found that the amount of tissue damage, the inflammation that occurred in their lungs and their alveoli sacs was a lot worse when the air was dry. And then the ability of the body to heal from that was also greatly reduced. The tissue repair was not as good when the air was dry. So this sort of thing has been really interesting to me, and I've been watching it for many years. I keep a hygrometer with me at my home, in my office, and humidify that space. But there's a big debate about having to have relative humidity up to 40% because it's not something that we're used to. We think about humidity as being sticky and wet and sweaty and smelly, or we think about ductboard with wet ducts and people getting aspergillus and infections and condensation on things. So we've grown up in a culture where humidity is thought of as a negative thing. but we really need to consider that buildings don't care about humidity. The building really doesn't care if it's drier or drier or drier. We really hate running humidifiers. They're challenging to operate, they're challenging to maintain. But if we start to think about the fact that people need that humidity, that indoor air hydration for health, we know that we can decrease infections, have fewer allergies, better wound healing, productivity is better. Even our stress hormone cortisol is produced not only by our adrenal glands, but it's produced by our skin. There's some research in Japan that researched that, and they found that dry skin produces a whole lot more cortisol than skin that's in a good indoor air hydration environment. So it's a lot about just having a mindset change and saying, you know what? Good humidification and humidifiers are more of a piece of infection control equipment than we ever realized before. And so we have to find ways to do a good job of designing them, a good job of how we control them, having safeties in place and maintaining them very carefully, thinking about preventative maintenance on them and not ignoring them, treating more like we do the emergency generators that we have to test every month and maintain and keep up really good, because we know in a crisis when the power's out, we want those generators to come on. Same kind of mindset with humidification, because it really can have an impact on health of occupants. ASHRAE has a web page with a lot of free resources and publications, and I think you would be surprised if you go to this web page at how many neat things there are available at no cost. This is one recent publication from a multidisciplinary task group about damp buildings and human health and how to avoid having a problem in a building. I know that some of the architects that I work with are really, really good with building envelope design. We know how to design buildings to be able to operate safely in 40 to 60% relative humidity. We do it all the time with museums and libraries, places like that. So it's not like it's impossible or rocket science. We just need to choose to do it. And we're starting to see more of that happen in office buildings and places where I want to have good relative humidity. The contrast to that is that some people aren't really great at designing building envelopes, especially in cold climates, to withstand those higher relative humidity levels. And so it's important in that case for people to seek out building science consultants or building envelope consultants, you might call them, who are really good at that and can help advise on the details of construction to make that successful. And then the people that are really good at it need to share their knowledge with others and help grow that capability amongst the design firms. So this is a little ploy on the original chart called the Sterling chart that was published back in the mid-80s, talking about the impact of relative humidity on viruses and bacteria, that sort of thing. Let's see if I can get my pointer over here. This 40 to 60% range is a good range for keeping viruses and bacteria at bay in many cases. And then now we have this microbiome study. We have the long-term care facility for elderly people and a preschool children's study that's really showing us the harmful effects of dry air. I didn't talk about these other studies. I could share them with you another time, talking about a project called Well Built for Wellbeing that I helped the General Services Administration with, where they looked at a 30% to 60% relative humidity range for buildings and what that did for sleep quality at night for people and their stress levels. So we know basically that 40 to 60% RH is good for health. So that's something we can do with our built environment to try to make it better. So if you're a facilities operator, maybe an architect, especially if you're in healthcare, these are some ideas of things that I put together as a little technical checklist on how to make a facility resilient and things we can be thinking about in the future. So we want to look at less expensive ways to prepare for a lot of patients when people get sick, so we're not having to convert huge convention centers into surge facilities, and then that's a lot of wasted dollars. So this ventilated headboard is a really great system that was developed by a colleague of mine with the CDC. So there's a YouTube video where you can watch how this works. It's pretty easy to put together, and it's been backed by research to show its effectiveness. People also need to practice and think about their plans of how they're going to handle epidemic scenarios. You know, every time people do simulations for that, they always seem to learn something new about their facility and the way that they thought things would go versus the way that they actually did. Sometimes we shed load, transfer capacity to one area of a facility or not. Out west, we've had a lot of wildfires in the last few years, and people are finally becoming a lot more aware of the cardiovascular burden of having wildfires. And we've had quite a few clients in the last few years that have asked us to design enhanced filtration systems for them that they can switch over to during a wildfire mode to help keep the air in their spaces clean. A lot of increase in stroke and heart attack for people when they're breathing that PM 2.5 air with all the particulate matter during a wildfire. So some of the things we do for epidemic preparedness can also be beneficial when we have wildfires going on, or when we just have really poor outside air quality from a lot of pollution or smog. We've got power outages we practice for, and then looking at doing procedures on infected patients. I've had a lot of healthcare people contact the epidemic task force. We provided guidance on how to do procedures on people who are infected with COVID-19. Encouraging people to look at their utility connections and how they're providing services for a facility. Certainly ramping up med gas capacity and oxygen, but potentially other gases in the future that might be important in a pandemic. When people are generating the need for more hot water, you got to wash your hands that whole 20 seconds. Not everybody's faucets turn on and off exactly the way they want, so you can be flowing a lot more hot water. Or if you're setting up facilities like for surge outside in tents, you still need to have hot water capacity for people to wash their hands. And kidney dialysis is another issue. We've had that extra kidney dialysis capacity designed into some intensive care areas, but oftentimes that gets value engineered out of a project due to budget constraints. And now some folks are wishing that they had more dialysis stations built in their hospitals for patients who've had kidney damage because of COVID-19. So some other checklist ideas. I think overall, when we're doing mechanical design, is to think about what kind of system are we going to select and what systems are flexible. At the start of the pandemic, a lot of people called and were looking for help on modifying their systems, increasing the ventilation, trying to have better filtration, doing 100% exhaust. And what do you do if it's not spring anymore and we're still in the midst of some of the changes we did to the system, and it's summer or it's winter and it's cold? We can't run the system the same way because the system doesn't have enough capacity to go into a 100% outside air mode during the dead of winter. So I think we need to consider more at the start of a project, what kinds of systems are more flexible than others and have the ability to be modified for pandemic type needs. Electrical outlets where you could put in UV light, for example. And then designing for 40 to 60% from the beginning. Asking ourselves questions like, how would we pressurize an area that's normally neutral or maybe make it negative? In healthcare facilities, where can people go step away and get a break and have some respite, or where can they don and doff all their gear? We learned a lot of healthcare infections, I think, happen from people trying to take off their protective gear, and they were generating aerosol in that area and then infecting other people around them. So having a good space for that is really important. Thinking about where the exhaust goes out of a building. If you run in 100% outside air economizer mode, you're essentially exhausting that space. But normally we just think of that air going out of a building as relief air, and it doesn't get treated with the same care as far as where that termination location is as it would if it were known exhaust. But if you're putting infected people in an area and exhausting that by running an HVAC system in economizer mode, you've really got to make sure that that relief air doesn't get re-entrained back into the building. And so ASHRAE is looking at code changes to permit some of the items above. We need to think about energy codes and say, how can we allow some of this inherent flexibility and capacity to be designed into systems without the restrictions that the energy code sometimes puts on us for saying, no, you can't design a coil with this much capacity because it's not necessary. Well, maybe not necessary in ordinary times, but I think we'd all agree that these are not ordinary times. And our most vulnerable populations are the people that are in healthcare facilities like long-term care, and we need to pay extra attention to them and remember that our buildings, I like this saying, are for people and not for saving energy. Energy conservation is really important. We have one planet and we need to make our resources last, but we also need to recognize that there are ways that we can do energy efficient things like increased ventilation and have an overall benefit in terms of people's health and productivity. So ASHRAE's Epidemic Task Force has a healthcare group, which I'm the leader of, and we have a separate subgroup working specifically to provide guidance for long-term care and hospice type facilities. I'm really proud that we're making a difference in that regard. I think we want to be asking ourselves, what would we do if someone in our family was infected and the rest of the family wasn't yet, and we wanted to put them in an isolation type space in a house? Can we confine them? What room would we use and how would we set that up? Got some advice on how to do that. And then I know some people in healthcare facilities or in offices were trying to think about how could they quarantine off a whole wing or a whole section of a hospital. And sometimes the architectural layout of the space made that easy. Sometimes it made it very difficult. That's maybe not something we've considered when we're trying to lay out the floor plan of a building early during design, but in the future, we need to consider that. And then working with clinical staff to think about, well, here's how COVID-19 presents itself, but what about another epidemic, another kind of disease? What might happen to people in that case, and what sorts of resources or abilities would we want with the built environment to help in that? So just some brainstorming needs to happen there. We've got natural disasters, there's the Cascadia Fault that's going to go someday, and then we've got parasites and prions and things like that to consider. I think the parasites are something we tend to overlook a lot. And this is my last little slide on resiliency checklist. It's a little bit bigger picture items, thinking about our Wi-Fi, our Ethernet capabilities, and how we would function during a disaster. Having a lot of isolation valves so we can close off systems, and having good drawings that show where those isolation valves are at. This image is from the Pentagon on 9/11 when the airplane crashed into it. And the image below that is a colleague of mine, Howie McHugh. Many of you that read Engineered Systems magazine will recognize his picture. Howie McHugh had the record drawings for the Pentagon commissioned when they were doing some work there. And because of his foresight, when the 9/11 disaster happened, they were able to close off and isolate some systems that were damaged because of the attack. And they were able to save quite a few lives because of the ability to respond quickly in that scenario. And people need to think about, how would I operate this if I can't get on my computer to look at the system? I need to do manual operation. What if I can't download product literature from a web page? Having hard copies of that is really important to think about ahead of time. And then this is just a quick little bit, but I've talked a lot to some other people more extensively about the public trust, what the level is of the public and their expectation, or when they walk into an office or when they walk into a healthcare facility in particular, what do they expect has been done to prepare for an epidemic? How is that air treated? They don't always realize what sorts of things have been grandfathered in, what sorts of things are only designed to a code minimum, but maybe not a best practice. And there's always that pull against the cost of a project. And there's also that pull against trying to design for resiliency versus trying to get more square footage in a building and just, I need this much space, I need this much program area. And I think we need to step back and say, how much area do we need and what are we willing to sacrifice in order to have more resilient buildings and to have healthier buildings, even if the program area maybe has to be decreased. But money talks. This is a financial analysis that was done on that Chicago hospital that was part of the microbiome study. And they looked at going in there and putting in humidification to design that for a minimum 40% RH all the time. And they made some assumptions that the system that went in was super expensive, a lot of costs for installation, really heavy cost on the maintenance. So tried to make those costs really high, and then assumed that a very small number of healthcare associated infections would be reduced because of that. And even with those real conservative assumptions, the return on investment was over 500% in the first quarter. So this really shows that the payoff is there and the benefits are just there for the taking. So the ASHRAE Epidemic Task Force is at this webpage down below. We formed in March, and we've created a lot of guidance for people. There are resources available and access to a lot of ASHRAE information that used to be for sale that right now you can access for no cost. There's a whole piece on building readiness, how to have a building facility operate in epidemic conditions versus post-epidemic conditions and back into a normal operation. So guidance for what do you do with energy recovery? Should you be turning off your energy recovery ventilators, or should you be running them? So lots of guidance available on that. And then we have specific building guidance groups that are looking at commercial buildings, healthcare facilities, residential homes, multifamily, and then a big piece that's been done and was recently updated on opening schools and universities, which is a big hot point right now. So there's also a little bit on transportation, some information if you're going to be traveling. So I encourage you to go to that webpage. There's a frequently asked questions section that you can look at, and you can also submit questions to the Epidemic Task Force and get answers to specific questions on that. So I've been busy responding to people from all over the world for the last few months about the pandemic. So this is just a closing thought. I like this t-shirt, that asteroids are nature's way of asking how your space program's coming along. We don't always prepare ahead of time. And I heard somebody say a long time ago, or read, that the easiest way to solve a problem is to deny that it exists. And I think we tend to do that sometimes when things get hard. We can just want to get away or bury our head in the sand. But preparing for a pandemic, it's something I've been thinking about for a long time. I sometimes catch a little grief from friends and family, but my team was joking with me the other day about how I had dressed up as a whole biocontainment unit Ebola fighter in my office for Halloween a number of years back. And so I guess maybe I was just thinking a little bit ahead, but it's really hard to predict and understand the scope of the magnitude of what's going on. Wanted to make a couple quick acknowledgements. Dr. Taylor, Bill Bonfleth, Luke Lung, Paul Bemis, and Dennis Knight. Bill, Luke, and Dennis Stephanie are all on the Epidemic Task Force. They've all shared some information that I brought along with you to share with you today. And so I just really enjoyed sharing what I have. Be happy to answer some questions. And this is a little picture of me in my office. My team showed to me a couple weeks ago, all set up, ready to go, masked up at work. This was, I think, in 2014. And then one other just kind of teaser thing to think about, we talked about technical ideas for resiliency and what we can do with our HVAC systems. But there's also a big component non-technically about what kinds of things can we do in our facilities with the groups we work with and how we interact with one another that can make us better prepared in the future. So these are blank because today isn't the day that we're gonna go over those, but I just wanted to give a little teaser for that if you're ever interested in talking about some of those non-technical ideas, because they can make a big difference as well. So with that, conclude presentation, and then maybe Jim, you could shuttle some questions along that we could look at.
We can do that. John's going to help me with that, actually. So Tracy,
Okay.
first of all, I want to thank you for your presentation, your information, sharing all that knowledge with us. I think it was fantastic. So I do want to ask everyone that's attending, if you have a question, please put it in Q&A. I see a few of them in chat. We'll try and look at both sectors, but please ask the questions in the Q&A so we can keep a little better track of them. So John, do you want to get us started with that?
Sure. Thanks, Jim. Tracy, we have about 10 questions. The first one was, what was the research paper where you went through total observed gene copies of the pre-filter and the diffuser? I don't think it was diffuser. I think it may have been dampers.
Oh, yeah, at the Oregon Health and Science University. Yep, I can share the information. I think the author's information was on there, but I got a copy of that via email. So, but I think that that's available with a web link. So I can look that up and provide that to access that. Mm-hmm.
And then another question was about how can we assure safety or a safe environment for employees working in open space areas? I mean, you sort of went through the filtering and outside air and relative humidity. Are there other steps for where workers are in open areas in a building?
Yeah, I think definitely wearing masks will have a big impact on that. There was a super spreader event at a call center that showed how a lot of people in one area became infected and they were not wearing masks. So people in open office spaces will benefit from wearing their masks because that greatly reduces the spread of those aerosol products through the air. In an open office environment, you're gonna have a lot more well-mixed air, and you're really concerned about that airflow between people before it gets back to an air handling system. You could have a great air handler with really good filters, and that's important to bring down the overall concentration in the space and ventilate that to, again, dilute contaminants even further so that it's perhaps below the infected dose. But that air just moving close between people who aren't that far away, mask wearing is real effective. You can also put in portable HEPA recirculation units and spread them out in an open work environment. You have to be careful about how you place those and where they're blowing air currents, where they're drawing air in from, but they can also help with some basically spot cleaning of the air. And I saw a model done by Paul Bemis on a webinar, and they did some CFD analysis of a space at a certain ventilation rate in a room with a whole bunch of people spread out at desks for, I think it was an hour or 2 hour time period. And then they put in 6 recirculating HEPA filter units in that space and then ran the model again. And they showed where that contaminant concentration in the space went down a lot. So, you know, masks are helpful for people to protect them from others, but masks also keep us from inhaling as many infectious particles. So I think that's a good plan for open office space. Certainly upper room UVGI could be beneficial as well for a space.
Very cool. Now, I like working with you because you've already answered the next question, I think. So the next one is, how much does wearing a mask indoors protect workers from getting exposed to the virus to mitigate indoor air risks? What I like about what you just presented was it's not about how effective one thing that we can do is. It's about layering that protection with like HEPA filters or UV exposure along with the masks. Is there anything else available on the effectiveness of masks or specific types of masks that you know of?
I do know there's a web page that I had looked at where they looked at different kinds of masks. The handkerchiefs are just not super effective. It's better than nothing, but they're not as effective as like canvas was really good. Denim was really good because they're doing a good job of blocking the particulates, but also having some breathability to them. So there's definitely some information research out there about different materials for homemade masks and what to make out of those. The thing that I've seen more talk about in the last month or so are the face shields. And so I've read some articles. There was a good article that was published a few years ago looking at the benefits of face shields. And I knew that, like, if I'm infected and I'm wearing one and I were to cough or sneeze, a face shield would certainly, well, probably get kind of gross, but it would protect other people from me a little bit better than nothing. But I didn't realize at a longer distances how beneficial the face shields could still be for people who are wearing them. I wouldn't suggest only doing the face shield instead of the mask, but the face shield really could prevent quite a bit of aerosol inhalation by a person. And so There are some facilities, I'm working with a local healthcare imaging place, and they're talking about having their mammography techs wear not only their masks, but a face shield, because when you go get a mammogram, I mean, the tech is just right there close to you, and having that extra barrier is really good. And if I were somewhere where I was really concerned about the infectious load around me, I would want to wear a mask and a face shield both. And they're coming up with some cool designs for those.
Cool. So with this discussion of filters too, what about maintenance workers and any protection that's needed for them when they actually go in to do either maintenance or filter replacements?
Absolutely. So the ASHRAE Epidemic Task Force addressed that. There's a section in there called Filtration and Disinfection. There's some specifics in there that you could go and look at, but I'll give you the quick summary, and that is definitely be wearing personal protective gear. Put on a mask, wear gloves, and you could put on coveralls if you have them, like little Tyvek, booties, that kind of thing. But at least mask and gloves, and then try to shut the air handling unit down when you go to change filters. I know some people walk into the air handlers while they're still running, and in some cases that's just kind of how it has to be, but it's best if the air handler can be shut down. And then some people take like a fixative, like hairspray or spray paint, and they'll spray the filters to just kind of fix everything on the surface of them. And CDC's seen a lot of people use that over the years for tuberculosis, and it's pretty effective. You can also take like a 10% bleach solution and spray the filters. You don't want to get them like soaking wet, but you can wet them down a little bit and get some disinfection of the filters before you change them as well. But hairspray works pretty good. And then just bag the filters up. No need to put them in hazardous waste. You can just throw them out in the normal garbage, but you want to just put them in a large bag as you're transporting them to your garbage bin. And then afterward, you want to make sure you're carefully removing all that PPE, washing hands. I've got some sanitizer that's in the spray bottle. And if I don't wear different shoes, like going to the grocery store, if I wear the same shoes back home, I spray the bottom of my feet before I come back into my house and let that dry for a moment on each foot, just to kill off the contaminants that can be on the floor. Because some of the studies that I've shown for particulates shows a really heavy load on the floors. So thinking about what you might set down on the floor and then pick up again, or just walking around on your shoes. It could be a source of transmission.
Okay. Let's go back to bringing in more outside air. Can you talk to any risks or anything that can deal with air pollution that might be drawn into a building as a result of that?
Mm-hmm. Yeah, one of the key elements of ASHRAE Standard 62.1 is to look at the quality of the outside air that's being brought in, and making sure that if it's got a lot of air pollution, a lot of particulate matter, that air is being thoroughly cleaned and treated before it's brought into a space. Just bringing in outside air could do more harm than good if it's not really properly cleaned. So having a good set of pre-filters, a good set of final filters on the air handling unit can make a big difference for that. So certainly want to pay attention to that outside air quality. Okay,
and then next is more of a comment. It's interesting that both relative humidity and temperature is also important for museum environments. So maybe there's some design lesson to learn from museum environments that we might be able to learn from.
Absolutely. You know, the people that do a lot of design for museums and libraries, those kinds of spaces, they understand the benefit and the health of that. And it's not that hard to do once you know. It just becomes part of your mode of thinking about those spaces and designing. You know, the codes for places doing animal research require the minimum 40% relative humidity, that 40 to 60% range for research animals, because they know that it's a super expensive monkey or whatever it is they're studying, and they want to protect the health of that animal. We know that it's really important for preserving documents and paintings and artifacts and things. Even the space station, they require the 40 to 60% relative humidity range. I say, what about the rest of us? Aren't we more valuable than a research monkey?
Okay. So this question is a little technical, I think, on VFDs or variable drives. Do you think they'll need to have larger ranges and become a mandatory feature of HVAC? And this is a layered question too. Will different buildings need modifications, and how will older buildings be impacted? Because they have a lot of older buildings that they're dealing with.
Yeah, I think the people that are occupying buildings are going to need to be thinking about those parameters. I would certainly be advising my clients and asking the question of saying at this time, okay, we're putting in this unit, here's the capacity, here's the static on the fan, these are the filters and the pressure drop, but what if we did something different? What if we replaced that with a higher performing filter? What's that going to do to the pressure drop and the required motor horsepower? So looking at that VFD capability, the incremental cost to change that is not that significant. We do need to pay attention to try and get good selection, so we have fans and pumps and stuff that are running at their most efficient range, but we can build in that extra surge capacity. And I think some people just don't think about doing it because, well, what's the point? It's just going to add extra money. Well, it could be really helpful in a pandemic, and the added cost might not be that significant. So I think we'll see more people evaluating that option and offering that to clients. And then when we think about existing buildings, going back and retrofitting that, a lot of buildings just don't operate as well as they were intended to when they were originally designed. We have things like over time coils that get fouling on the coils, and so we just don't get as much heat transfer through them as much as was originally designed into the system. So we can go in and retro commission facilities, look at them and say, here are some things we can do maybe with the control system and how things are sequenced. Maybe we change out some coils and put in a new coil that's in better condition, and we build a little extra capacity into it at that time. It helps to think about what a facility's infrastructure is like before it becomes critical to replace items. Because if a chiller fails, most often someone comes in, takes that chiller out, puts the same kind of chiller in as they had before, maybe upgrades the refrigerant to meet new codes, but they don't always take a big picture look about what could we do with an overall system infrastructure improvement. You have to have some time and some evaluation and assessment done in order to make a good decision. So it helps to get somebody involved on the front end to do that kind of assessment, to think about what that might cost and to plan that in. And then you're not left scrambling trying to upgrade something that's just failed and needs to be replaced right away because you have people getting hot or cold in a building or something, you're worried about freeze protection, something like that. So I think we'll see more and more of that. And then one last thought on that is when you think about real estate, I think more people are going to be asking questions about the building that they're in. And when their leases are up and they start looking for new spaces, they're going to ask, what's the filtration rate in this building that we're thinking about for our office? I think employees will start wondering what the space is like that they're working in and demanding more. So it's going to behoove people who are trying to recruit the best and brightest employees or to be able to lease a building out to pay attention to some of those things and try and have the built environment be optimized for people's health and productivity rather than just saying, yep, it's quiet, or you don't hear it, you don't think about it, and that's good enough.
Okay, I'm going to combine three more on filters. I think you've addressed parts of these, but if you were to recommend switching a building's filters to a particular type, what would it be? Are there additional guidelines for replacing and disposing of those? You already touched on that. And like, as an example, how often should you replace a MERV 13 filter? So can you go over some of those filter, I guess, basics if you were looking to replace one?
Sure. And again, that ASHRAE filtration section has a lot of good guidance in that you could follow up with. But filters that are like 1 or 2 inches thick usually need to be replaced about every 3 months. The more a filter loads up, the better job it does at catching things because it's more cloggy, if you will. But if it gets too loaded up, you don't get the same amount of airflow through the filter, and so then you have other negative consequences. So you can watch the filter and look at how dirty it's getting, but usually about every 3 months is a good time frame. Filters that are a 6 or a 12-inch deep filter can go much longer than that. And usually those systems are equipped with a pressure gauge that measures the pressure on either side of the filter and measures that pressure drop across it. And the systems are usually designed to have a certain amount of pressure drop across them before they're changed out. So that's a good way to think about it. But some of those filters could go 6 or 9 months. I work in a building that's next to a bus plaza. And one day there was a guy that got on the elevator, one of the facilities guys. He was getting ready to go change the filters in the building, and I was visiting with him. He was all set up in his PPE. This was early on in the pandemic, and he said that he changes the filters there every week just because there's such a huge load from all the traffic of people coming in through the bus plaza. And he's like, yeah, no kidding. If I go more than a week, the filters are just completely caked. So every facility is a little bit different on that. I think there was one other part of the question that you asked. Maybe you could repeat that for me.
No, I think you touched on all of it, other than the type, like if you were going to replace it.
Yeah.
Yeah.
We're recommending that people try to get at least a MERV 13 as a minimum level of filtration. If you can do better, that's great. MERV 14 is the minimum level. We used to call it like, fell down. I'm in somebody else's
Didn't
office.
like that one.
Yeah. A MERV 13 filter, kind of the minimum. The 14 is the minimum level for a healthcare facility. We used to call that a 90 to a 95% efficient filter. And then of course there's HEPA, and we do have people that use various levels of HEPA filter, especially when they're trying to filter out the really fine particulates for like a wildfire event and cut down on the PM 2.5 level in a space.
Mm-hmm. Mm-hmm. So another one is sort of related to filters, but it's UV lamps, their use, and if you would put them upstream or downstream of filtering.
So the UV lamps, there's a few different ways to do that. The in-room UV, upper room UV GI can be pretty effective. It's been well proven for years for things like tuberculosis. So that's one option, and you don't have to have real intense bulbs. The effectiveness of UV is partly the contact time and partly the intensity of the bulb, and there's an equation to figure that out. So if you have upper room UVGI where that light's going all the time and air is circulating through a space, the bulb intensity level can be pretty low and the power requirements can be pretty low because that air is going to be moving by slowly and have a lot of time to be exposed to that light. You can also do those systems inside an air handling unit. You could do them upstream or downstream. In a retrofit, that probably depends just on the space and configuration available. But because the airflow is very fast, moving through ductwork or through the different components of an air handling unit, you have to have really intense UV light bulbs in order to kill or inactivate a virus or bacteria in the short amount of time that that air is passing by. So that's a special design to think about. We do see oftentimes people that put a UV light on a cooling coil downstream of the cooling coil, shining that back up at the coil to try and keep mold and growth from building up on the downstream side of a cooling coil, which gets wet from the condensation. Those bulbs are not going to be nearly enough intensity to inactivate a virus that's going by quickly. So that doesn't really help there, but it does help keep the cooling coils clean, and that's pretty effective. So thinking about it in the duct or in the air handling unit, it has to be a pretty decent length section to allow enough contact time and some pretty intense bulbs. So the power requirements can be significant, but it's effective and it can inactivate viruses. One thing that I like about the relative humidity piece and keeping that 40 to 60% relative humidity is that microbes don't seem to develop a resistance to relative humidity. Whereas microbes that have been up, like studied in the space station that are exposed to UV light, over time have been shown to show some resistance to the UV light. So I think that the UV light is effective, but long-term, I have some concern that we might see some microbes that develop a resistance to that, where it might not be as effective in the future, years from now, as it is at this time.
Mm-hmm. Has anybody looked at operable windows and how that might affect transmission?
Yep, it's not an area in the United States that's studied or utilized nearly as much. Europe certainly does a lot of natural ventilation,
Mhm.
and people are a little better versed in the design communities over there with it. But definitely having operable windows can benefit, provide more ventilation. The caution really with it is, what is it doing to the room airflow pattern? Some people think about opening a bathroom window up. And the problem is like if you had a house and you open the window in the bathroom and then you're out in another part of the house, opening that window could cause air to come into the window and then draw contaminated air from the bathroom out into the rest of the house instead of having it go out through like an exhaust fan in the bathroom. So sometimes the airflow direction is just harder to control. And then of course, if your outdoor air quality isn't good, then you wouldn't want to be opening up the windows. But certainly having that fresh air, and you could open windows, it's great because it also greatly increases the diversity of the microbiome. And that's a whole nother area that we could talk about of the microbiome and the diversity of that and how it affects our mental health, affects our digestion, our cardiovascular system, all kinds of things like that. So I do worry about us super cleaning everything all the time and knocking down the diversity of the microbes. But for the short term, I think that's the better decision.
This one's sort of linked, but haven't U.S. energy conservation guidelines created buildings that can't function in a COVID contaminated environment? And this one is interesting to me because I'm on the energy side now. But so from my perspective, the flexibility that you talked about can actually be used as an advantage on the energy conservation side too. And my opinion is we keep trying to design to a specific design point when the flexibility is where the real value add is going to come in the life cycle of that system.
Yeah, I agree with you completely that if we think about it early on and you use things like energy recovery type systems,
yep,
we can have flexible systems, we can increase that ventilation rate, and we don't have to have a building that uses a lot of energy, and we can keep that reasonable.
Yep. Do you have an opinion on the relative transmission rate of aerosol to droplet? So 10% aerosol versus 90% droplet, or is there?
I wish I knew the answer to that, and I don't, but I did see something recently that was a study that was done on the cruise ship where they had a big outbreak.
Oh, yeah.
And this group ran a bunch of different simulation. They collected information from people about when they were sick, where they were at, their movements, their habits. They got as much information as they could. And then they created a computer simulation that said, okay, if this person was generating aerosol, this person was touching things, maybe there was a short distance droplet, there was the fomite contact, or there was maybe a longer distance aerosol transmission going on. And they created a whole bunch of different models, and I wish I could remember the number. I want to say like 1,200 or something like that. And they ran them all, and then there were only a few, like less than 100, that had outcomes that matched the reality of what had happened on the ship with who got sick during what time frame. And so they discarded the other ones and focused in on the remaining and then fine-tuned those. And the results of that showed that about a third of the infections were probably caused by a fomite type transfer, about a third of them from a short distance droplet, and then about a third of them could only be explained by a longer distance aerosol transmission that happened beyond the 6 feet circle that we all think about. So that's the only published study that I've seen to try to quantify that, but we would really like to get a better idea of how big of an impact that longer distance aerosol transmission plays. I think there's a lot more growing consensus that this is a factor when we're talking about people in one room that has more occupants and poorer ventilation, that the 6 feet circle isn't enough. And we have to take other precautions with masks or trying to increase the ventilation or clean the air. I think the question goes even further into the unknown when we start talking about what happens to the person in the office next to mine or in the room down, the patient room down the hall, and they're all in the same air handler, are we seeing clusters or cases where people came in maybe to a hospital, someone was in a room where they were pretty much kept to themselves, but they still got infected while they were in the hospital? Unfortunately, that data is really hard to get, because if a healthcare associated infection can be explained by any other contact, potential friend of a friend or something, that's probably how it's going to be looked at, because healthcare facilities don't want the public to be thinking that their facility isn't safe, and that just getting that kind of information to be shared, it's hard to come by. But we really need people to be as open as they can about those kinds of events, because that's how we learn. And if it's happening in one facility, it's probably happening in another facility, and sharing that knowledge can then help us say, hey, we really need to take more precautions than what we were taking before in order to stop this from happening.
So here we are, the last one, and I thought my engineering background was going to help me, but only so much. So I'm going to try this one. Is MERV 13 or higher if it's not possible in a variable refrigerant flow cassette or a unit fan coil unit found in most classrooms? Would, and here's where I'm lost, DBD bipolar ionization be a safe and effective alternative to filtering?
I would recommend trying to increase the ventilation or the filtration rate. Those VRF cassettes, that is a detriment of those. The ceiling cassette ones in particular, I think can only do about a MERV 10, maybe 8 or 10, something like that. Some of the better classroom units I know can go up to a MERV 10. So I would get that as high as you could. I would increase the ventilation rate and size those systems to provide more outside air, put better filtration, at least in the DOAS unit that's serving the VRF cassettes. And then I'd start looking at spot treatment with HEPA filters, recirculating room units, or UV type systems. I personally wouldn't go with the bipolar ionization. That technology has been around a while. There's not nearly the amount of peer-reviewed published literature on that technology as there is on things like UV light that's been pretty well established for a long time. The ASHRAE position document on infectious aerosols mentions UV, but not bipolar. And they're not specifically saying no. I know ASHRAE has to be careful about not endorsing or unendorsing a product, but when you look at really good peer-reviewed literature and you're trying to figure out, well, was this piece of equipment tested the same way that it's going to be used? Was there a baseline control comparison for the product to see how effective it really was? In the absence of it, was the performance just as good, or did it really make a difference? A lot of that information is lacking, and there's controversy over it. Some people are saying that bipolar ionization creates ozone in a space, which obviously has damaging health effects, also can contribute to a buildup of carbon dioxide in a space, which is not great. So just the jury's still really out on how effective that is. And I think time will tell, but I know that's a product that's been pushed a lot lately during the pandemic. So we'll see, but it would not be my first choice, personally. Well,
Okay.
I'm not.
I think we've exhausted all the questions, maybe exhausted you too, with the extended time that we put in here. I mean, I thank you for answering all the questions and answering them so completely, as well as a wonderful presentation. So, thank you very much. We do have a survey to send out to all the participants to get your feedback and ask about other topics that you would like to hear, including a more detailed discussion of this potentially, or of the previous pedestrian planning some webinar that we gave to talk more about some engineering tools perhaps that could be available to designers of these designer factors, I guess. So Tracy, thanks very much. Any last words from you?
No, just Thank you for the opportunity. It was good discussion. I appreciate all the questions everyone had. So feel free to reach out if you want to have some more conversation. Have a great day.
Okay, thank you all.
Yep.
And we'll bring this to a close then. Thanks very much.